Hey everybody, sorry for having to do class this way. I know it's not optimal. I will try to make this as brief as possible because I know it's obnoxious to watch a video. Um, Before I dive into the material, just real quick, if you fill out the idea forms for the course and take a screenshot of the submission page and then send me an email of that, you'll get 3 bonus points on your final exam. So there's some bonus for filling out the idea forms and then showing me evidence that you did that. Okay, so chapter 15, we have to very briefly cover it. This chapter always breaks my heart a little bit because I would like to spend 2 or 3 weeks on this topic, and there's not time. So we're going to spend 2 days on it. But Markov chains are super nice. They're such a sleek, elegant, probabilistic tool. And they come up in all sorts of places if you think to look for them, or if you think to frame problems that way. So I really like them. I'm going to give you a taste of them as a way to end the class. Applications are from games to actually, if you go back to that paper we looked at for the Pennsylvania gerrymandering analysis of the Pennsylvania congressional district maps, the way that this author, Moon Duchin, the way she did her outlier analysis, her hypothesis testing, was she used Markov chains. We did not delve into the details of that at the time, and we won't here either, but we could have actually, given this section, we could if we had time, but we don't have time. Anyway, so just to motivate what these things do for you, I should say that in these handouts I added some images that I would write on the board, so I apologize for the low quality of the images, but anyway, so the handout is basically filled out here. Okay, so here's a motivating example. All of you parents out there, right? Several of you have kids, maybe, I don't know. Probably not, but this example will resonate with any parent. When you have a kid, their health exists in 3 states. They're healthy, they're sick, but you can still kick them off to daycare if you want to. You know, like you got to go to work. Really, it would be nice if that kid would go to daycare, and then they might be too sick to go to daycare. So 3 states of existence for my kid's health, and then here's a little model of like how he might switch from state to state. So let's say that I've looked back on past data, I've kept really good records, and I've noticed that if he's healthy, there's a 90% chance he'll be healthy the next day. So if he's healthy today, most of the time he'll be healthy the next day, an 8% chance that he'll be sick, but I can still send him to daycare the next day. If he's sick but healthy enough to go to daycare, there's a 50% chance he'll stay at that level of sick for the next day, and a 20% chance he becomes too sick to go to daycare. If he's too sick to go to daycare, there's a 1 in 3 chance he stays that way. 64% chance that he'll still be sick but healthy enough to go to daycare, kind of recover some. So given this kind of description of my son's health, we could ask all sorts of things. So here's a question. On the Wednesday of spring break, my son was sick, and I couldn't send him to daycare. That was okay because it was spring break, so I can stay home and take care of him. But it sure would be nice if by the following Monday, when I go back to work, for real, right? I'm still working from home, but when I have to be in class, be nice to send him to daycare. What's the probability of that? If he's healthy today, what's the probability he's healthy any amount of time from now? 2 weeks from now, 3 weeks from now, whatever. In the long run, how often is he healthy? Okay, so questions like that. So there are lots of ways to analyze a problem like this, but for me, the most natural and the most elegant is to use what's called a Markov chain, and it looks like this. It's a network. So in a network or a graph or what's another word for it? I call this a graph, but people outside of math like to call these things networks. I have nodes which represent a state of being. So like a node here, a node here. The circle is a node. It represents a state of being. And then the arrows show possible transitions between states of being. And you decorate the arrows with the probability. So this is saying if he's healthy today, like one move along one arrow is 1 step in time. So a 90% chance healthy tomorrow. So we can think of my son's health. Like if he's healthy today and you want to think about 2 days from now, 3 days from now, imagine there's a token on this H. And 3 days from now means we've taken 3 steps through this network. So maybe he's done this move, this move, this move. Maybe he stays healthy all 3 days. Maybe he moves to this kind of sick so he can still go to daycare. But then he goes back to healthy and then stays healthy. So 3 days from now, 5 days from now represents that many steps through this little network once you give it a start state. So if he's healthy today, you would put a little token here, and then imagine the token moving through this network. So a picture like this, where you have states of being that are these little circles and transition arrows decorated with probabilities representing one-step probabilities, so one step in time, that's called a Markov chain. Okay. Given a Markov chain, what you'd like to do is take it and then create something purely mathematical from it that you could feed into a computer. So what we're going to do is we're going to take that picture and make a matrix out of it. So I've labeled the states here A, B, and C just for simplicity. So A is healthy, B is kind of sick, and C is too sick. So see, this is saying, the way you read this matrix is, if I want to take a step from A to A, so the from is in the row and the to is in the column. So from A to A, there's a 90% chance of that. From A to B, there's an 8% chance of that. So therefore, there's a 2% chance he goes straight from A to C. From B to A is a 30% chance. So from B to A, let's come back up here. From kind of sick to healthy, there's a 30% chance, and so on. So I guess all I'm saying is back up here, there are 9 arrows if you count them up. And if we order the states in some way, it doesn't matter. It's arbitrary, but so I could have had C be H here, but whatever. I order the states, and then I'm consistent in ordering column and row. I can just put the probabilities from those 9 arrows in this matrix, and this is called the transition matrix. And this is what will hand a computer to analyze probabilities for questions like what I have above. Okay, so whenever you study Markov chains, this is always the punchline, that if you can model your process like this, with a picture like this, so not all problems, not all probability problems can be modeled like this, but this state of being of my son's health can be modeled like this. If you can model your problem like this, then you can create a matrix, and then it turns out this matrix tells you everything as long as you're willing to do some linear algebra. Linear algebra just meaning the study of matrices. Now, some of you have not taken linear algebra. That's okay. We're going to shove all the theory under the rug because of that. But basically, linear algebra is a nice field of math because it's very amenable to computer analysis. It's very computable. So once you have this matrix, you can hand this matrix to a computer, and the computer does all the heavy lifting for you. Okay, so now let's think about, suppose right now you're in some state of being, and you want to think about the probability you'll be somewhere else after a certain number of steps through time. It turns out if you want to do that, all you have to do is take this matrix and multiply it by itself n times. So you can always multiply a matrix by itself. If you don't know how to do that, that's fine, because the computer will do it for us. But it turns out that this matrix multiplication encodes all the possible ways of getting from state I to state J in n steps. Okay, so what do I mean by that? Let me just illustrate real quick back up here. Suppose my kid's healthy today, and I ask you, what's the probability he's healthy 2 days from now? One thing you could do is say, okay, I will analyze all ways of starting at H and ending at H after 2 days. So I could do this arrow and this arrow again. The probability of that is 0.9 times 0.9. Or I could go from H to kind of sick and then back to H. The probability of that happening is 0.08 times 0.3. Or I could go from H to too sick, so 0.03, and then back up times 0.02. So there are 3 ways to start at H and end at H in 2 steps. So you would just add up the probabilities from those 3 ways, and it turns out if you did that, you would get this number right here. This is the probability of starting at A and ending at A after 2 steps in time. So the matrix multiplication takes care of the or, like this way, or this way, or this way. The matrix multiplication adds up all those possibilities and spits out the answer. So I could ask you, like, hey, if my kid's kind of sick right now, 2 days from now, what's the probability he'll be healthy? So going from state B to state A in 2 steps. You would go, oh, here's state B's row is the middle row, state A is the first column. So there's a 43% chance-ish that 2 days from now, if he's kind of sick, he'll be healthy. Which is the most common outcome, actually, right? So there's a 40% chance he's still kind of sick. There's a 17% chance that he's too sick to go to daycare after 2 steps. Okay. So, I mean, this is just super nice. And I don't... Oftentimes, I don't know how to properly motivate how nice things can be. You can't fully appreciate how nice this is until you've done it. And maybe it's your research or something, which is what I've done. It's just beautiful that the matrices work like this. Um, so like I said, we can only see this for 2 days, but really nice. Okay, finally, if you want to think about what happens in the long run, like if I want to take sort of infinitely many steps, what proportion of the time is my kid healthy? What proportion is he kind of sick, and so on? You can use a Markov chain calculator, and I have one on Brightspace. So if you go to Brightspace, Markov chain initial calculator, let me show you what that does. Okay, so it brings up this website here. And so notice, first of all, it lets you think about number of steps in the future. This is number of time steps, so I'll do 2 steps. It lets you type the transition matrix. It defaults to 2 states. So for our example, we got to insert state, get another one going. And so then you would just type in the matrix. Let me find it. The initial transition matrix, so 0.9, 0.08, 0.02, 0.3, 0.5. Notice the rows have to add up to 1. The columns do not have to add up to 1, but going from A to A to B, A to C, that exhausts all possibilities. So you type in the matrix, and then you tell it your start state by putting a 1 in that column. So this means I'm starting at state 1. So that would mean my son is healthy initially. If you want my son to start kind of sick, you would put a 1 here in state 2. Anyway, so let's say he's healthy today. If you hit calculate, it tells you, because I had 2 steps, right? So it tells me 2 days from now, there's a probability, so 83% chance that he is still healthy, 12% chance that he's kind of sick, and a 4% chance that he is too sick to go to daycare, which I think corresponds to this, right? So this calculator is showing you that. Okay. Now it also gives you this information. See, steady state vector. So what that's saying is, that's the t goes to infinity question. Over time, just what proportion, given the initial model, that initial transition matrix, what proportion of the time will he be healthy? About 69% of the time. What proportion of the time kind of sick? 22%. And then like 9% of the time he'll be too sick to go to daycare. That's what this Markov chain model would predict. So anyway, if you want to ask, like, well, 4 days from now, if he starts healthy, I'm going to start him healthy, 4 days from now, what's the probability he's still healthy? 75% chance now. 17% chance that he's too sick to go to kind of sick, and then a 6.5% chance that he's too sick to go to daycare. So you can just use this if you want to calculate Markov chain probabilities. Okay. So since the calculators will do all the heavy lifting for us computationally, really all I want to focus on today and next time is, given some sort of scenario, can we recognize there's a Markov chain there? And that takes some practice, and we're just not going to have a lot of time to practice it, so, so we can't get too deep into it. But anyway, I want to quickly show you a few examples that at first glance don't look like anything in particular, but you can model them with a Markov chain if you want to. So here's an example. A rat runs through this maze below, let's say every minute or every second. It doesn't matter, but each time step, it leaves the room it's in and it goes somewhere else, chosen at random. So if it's in room 3, it will go to room 1, 2, 5, or 4 at random on its next move. So how would you model something like this? Well, you can think of each room as the rat's state of existence, and it transitions from state to state via this, like these doorways. So here's a Markov chain that models that kind of thing. And notice I've drawn it geographically, matching the original picture. Like state 1 is the northernmost state, and it's by, you don't have to do it like that. Like you can draw this however you feel like. You just need to respect the physical nature of the scenario. So like if the rat is in room 1, it's going to move to room 3 guaranteed, because it leaves the room it's in and goes to somewhere adjacent. And there's only one adjacent room, 3. Same thing with 2. If it's in room 2, it's guaranteed to be in room 3 at the next step. If it's in room 4, it flips a coin between rooms 3 and 6. So anyway, that's what this is showing. If you're in room 4, flip a coin. Go to room 3 or go to room 6. Okay, if it's in room 3, it has a quarter chance of going to any of the adjacent rooms. So there's a Markov chain that models that. So we could ask all sorts of stuff. If the rat is in room 5, what's the probability that 9 steps from now it's in room 6? You know, whatever. So I think I have this one preloaded. So just to save time, I preloaded this one. I typed in the transition matrix. So from state 1 to state 3 is guaranteed, you know. So you can verify that this matrix is correct. And I'm starting it in state 5, in room 5. And I want to go 9 steps from here. Right, so 9 time steps. If I hit calculate, okay, so what was the question? I don't remember. 9 steps from now, it's in room 6. Okay, so there's a 1/3 chance that after 9 steps, it's in room 6. And there's a 2/3 chance it's in room 3, and it's impossible for it to be anywhere else. So how nice is that? Again, like, wow. So neat that the matrix multiplication just does this for you. Because if you go back to this picture, if you wanted to sort of like case by case exhaust this rat taking 9 steps, so okay, it's in room 5. You could be like, all right, well, how would it do 9 steps? I guess it could go 1, 2, 3, 4, 5, 6, 7, 8. No, I messed it up. How does it even? Oh yeah, 9 steps, right? What's the probability it's in room 6? So here's one way to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. You could do it that way. It could go 1, 2, 3, 4, 5, 6, 7, 8, 9. It could go 1, 2, 3, 4, 5, 6, 7, 8, 9. There's many, many ways that this rat could take 9 steps and end up in room 6. We don't want to think about all those possible ways and add them all up, do we? That sounds like a nightmare. But the matrix multiplication, just like it takes care of all those cases. Okay. Also in the long run, so let's answer that. So it gives me the steady state vector, but notice now actually it tells me something. It says steady state vector does depend on the initial state. So it here, if we start in state 5, the 9-step vector corresponds to the steady state vector. So in the long run, if you start in state 5, you're going to spend 2/3 of your time in room 3, and 1/3 of your time in state 6. But there's some kind of like even oddness happening here, right? There's no good limit in this answer because like back up here, if I take an odd number of steps, I could always be in room 6 if I feel like. If I take an even number of steps, I could always get back to state 5. So this problem here, there's not a great answer to this question. What proportion does it spend in each room? Because it does depend on where you start and how many steps you're taking. So it's not like you can always answer a question like this. So if you see the calculator being like, well, it kind of depends on where you start, and it gives you a bunch of different answers, that's telling you that there's some sort of parity issue or something that you can't fully predict a clean steady state vector like we did with my son's example. Okay, let me show you a couple other examples. This one, if we were in class, I would give you 10 or 15 minutes to think about, but because I'm making a video, I'm not going to. You could pause the video and see if you can figure it out. I'm showing you this one. It's kind of complicated, but I want to, again, emphasize that Markov chains, like that kind of model, can show up in unexpected places. And then once you recognize there's a chain there, then the matrix thing just takes over. It's just a computational problem at that point. So anyway, this doesn't look like a Markov chain problem or any kind of problem really, but you can model it that way if you want to. So anyway, you got 2 machines that are parallel. One of the machines is needed, so one machine is off while the other one is on. But there's some chance that a machine breaks, and so then the other machine would turn on, but maybe it breaks. So anyway, there's a 5% chance that a running machine will break, and then you got to take 2 days to repair it, and production will shut down when both are in need of repair. So it says here, use a Markov chain. I'm just going to show you the chain for the sake of time. I'm just going to show you the matrix, but what you really need to think through in a problem like this is like, what is the state of existence for this process? Like if I freeze time, 5 days from now, right? What would the state of existence look like? So for example, here's a state of existence. Machine 1 is running. Machine 2 is not running, but it could run if we needed it to. It's not broken. It's not being repaired. So machine 1 could be running, and then machine 2 could be not running, but could be turned on if we needed it to. Machine 1 could be broken. Machine 2 could then be running while machine 1 is being repaired. There's all sorts of different states of existence. So let me just show you the Markov chain. Make it fit. Okay, so R means running, B1 means broken, but for a day. It takes 2 days to repair these things, right? And being broken for 1 day is worse than being broken for 2 days, because if you've been broken for 2 days, that means your repair is almost over. So you keep track of the timing. IR means in reserve, so it's not broken, but it could turn on if we needed it to. So initially, machine 1 is running and machine 2 is backup. There's a 95% chance we stay in that state, but there's a 5% chance that machine 1 breaks. Okay, well, if machine 1 breaks, it's now been broken for 1 day, and now machine 2 is running. Okay, so now if machine 1 has been broken for a day and machine 2 is run for a day, there's a 95% chance machine 2 keeps running, but notice there's no arrow here. Because the machine 2 keeps running, we keep track of the fact that now machine 1 is in its second day of repair. Okay, so from there, what could happen? Well, things could keep churning along nicely for machine 2. It was running here, it was running here. There's a 95% chance machine 2 keeps running, and now because machine 1 has been broken for 2 days, the repairs are over, now it's in reserve. And then we just get kind of a mirror image of that with machine 2. So now machine 1 is in reserve, machine 2 is still running. Now machine 2 could break, and we get kind of a mirror image. And so notice here, here, okay. So from this state here, machine 2 running, machine 1 been broken for a day, there's a 95% chance that machine 2 keeps running, but there is a 5% chance that machine 2 breaks also. So we get a state that looks like this, where they're both broken, like they're both being repaired, but machine 1 is in its second day of repairs, whereas machine 2 is in its first day of repair. That's kind of a different state. Like you can't just say they're both broken. You have to keep track of how long they've been broken. But notice if you're in this state, if they're both broken, but machine 1 is about to be fixed, then the next day you're guaranteed that machine 1 is broken and machine 2 enters its second day of repairs. So this is the kind of matrix, or sorry, the kind of Markov chain that, like it's hard to conceptualize this if you haven't had practice with this kind of thing. So like I said, normally in class, I would give people 15, 20 minutes to think about this and maybe try to discuss our way into something like this. So this isn't the kind of thing you just sit down and write unless you're used to it. So like I've spent time thinking about Markov chains, so I just spit this out. But I've had a lot of practice and a lot of time thinking about it. But here, here again, like the original English doesn't suggest really that you could draw a diagram like this and then get a matrix going, but you can. Now, if you want to use a calculator, there are what, 1, 2, 3, 4, 5, 6, 7, 8 states. So you would label this A, B, C, whatever order you want, A, B, C, D, E, F, G, H. And you could still use that online calculator. You would just get an 8x8 matrix, and most of the entries are 0. So I should have said that up top, but like back up here, I mean, I guess there is an arrow from 2 to 1, but its weight is 0, so you don't draw it. So anyway, here there's a bunch of entries that are all 0. So you could feed this into that Markov chain calculator and answer whatever you wanted. Okay, finally, let me show you one more craps, and we're going to use this next time. So if you don't remember the rules, you roll 2 dice. If you roll a sum of 7 or 11, you win immediately. If you roll a sum of 2, 3, or 12, you lose immediately. Otherwise, that initial dice roll sum is the point, and you go into a second phase where you keep rolling until you roll the point, in which case you win, or you roll a 7, in which case you lose. So you can model this game with a Markov chain like this. Now, it's too big to draw the whole thing, and you might be thinking I've overcomplicated things here, but it's actually really nice. Like there's a lot of symmetry, and I have to do the ... because you can get more points than just 4 or 5. You could roll a 6 initially, you could roll a 10 initially, but notice you have some initial start state where we haven't rolled the dice yet, and from there you could just win immediately with a probability 8 over 36 by rolling a 7 or an 11. the probability of that happening is, okay, so getting a 7 is a 6 out of 36. This is a 2 out of 36. So there's an 8 out of 36 chance you win immediately, but there's also a 4 out of 36 chance you lose immediately from getting a 2, 3, or 12. Otherwise, you roll a point, and I forgot to label these arrows. This arrow here, the probability you would write is 3 out of 36. 3 out of 36 is the probability of rolling a 4. And then once you've rolled a 4, you go into that second phase. Either you roll a 4 again, the probability of rolling a 4 is 3 out of 36, and you win, or you roll a 7, and the probability of that is 6 out of 36, or you roll neither of those, and you just stay in the state. This like continue game state. And the probability of that on a single roll is 27 out of 36. Similarly, you could roll a 5 up front, and I again forgot to label the arrow here. That's probability 4 out of 36. So once you roll a 5, now you're in this phase where like either you roll a 5 again, and the probability that's 4 out of 36 and you win, or you roll a 7, in which case you lose, probability is 6 out of 36, or you roll neither of those and you just stay in the state of continue the game, and the probability of that's 26 out of 36. So this ... encompasses all the other points. Like the point could be 6, the point could be 8, 9, or 10. So there's 4 more states over here. This says practice for next time because next time we're going to talk about what are called absorbing Markov chains. And notice here, there are these kind of terminal states, win or loss. And here the question we're interested in is, what's the probability I make it to the state W? There are lots of ways to get there, like I could get it straight off, but I could roll a 4 and then not roll a 4 or a 7 for a long time and then eventually make it over to win. There are like infinitely many ways to start here and then get to W. So the probability is the question is, what's the probability I make it to W versus what's the probability I make it to loss? So we already know the answer from chapter 3, but this is actually, despite my crappy drawing here, this is actually a much cleaner way to think about things than chapter 3. And once we get our matrix set up, the answer will just fall out. So we'll see that next time. Okay, so that was a brief intro to Markov chains. Hopefully this wasn't too long. I didn't time myself. Remember that you can get extra credit on the final if you fill out the idea forms. If you have questions on anything, shoot me an email or we can talk about it on Friday.